This talk by Sujatra is very interesting. It's very relevant to this year's El Nino because the major issue in the Pacific is the gradient along longitude. But somehow, not many papers are that. I can give you 100 papers to talk about gradient in latitude. We have done a lot about this, but Pacific, this is very important. And so this work is very interesting. So let's hear it.
Good afternoon, everyone. I'm Sujatra Bhattacharyya, and my supervisor is Professor Chakraborty. So today I'm going to talk about this recent work on this role of the Pacific zonal SST gradient on South Asian summer monsoon in Aquaplanet simulations. So at the very beginning, I just wanted to show this is the classic picture which in the tropical dynamics people generally show. So this is the precipitation. So this is the precipitation, the tropical precipitation belt, which we generally call as the intertropical convergence zone. And I have intentionally kept this region, this particular domain, because we are talking mostly over the South Asian domain, what is the variability which is associated with the Pacific gradient. So this is from the observation, as you can see that in the winter time, December to February, this seasonal tropical rain belt is to the south of the equator, and in the spring from March to May, it goes slightly northward towards the equator, and during the monsoon season, Boreal summer, June to September, it is far more to the north of the equator, over this Indian land and this particular region or the Western Pacific. And several literatures have shown that the seasonal meridional migration of this tropical rain belt, which is known as the intertropical convergence zone, is actually responsible for the monsoons, which several people have shown using energetics framework as well. So I try to see the ITCZ, which previous papers have also seen how this rain belt varies as we change the SST maxima. It has a zonally symmetric SST pattern, and we can generate the intertropical convergence zone. So at first, we have used this actual July sea surface temperature condition, and we have just zonally averaged it. So this is now the meridional variation of the blue one is the meridional variation of this actual July SST. And as you can see that the peak of this is around 7 degrees north, which is just to the north of the equator during the July. And with this and this solar insolation, which is typically the summer solstice kind of a solar insolation condition, we generally get this ITCZ or the tropical rain belt just to the south of the equator. We cannot make it through the north of the equator. This has been shown, I think, in the Prive and Plum 2007 paper, where they have shown this kind of a result and try to explain it using the moist static energy advection and all. Now, what we did is that since we require this ITCZ to the north of the equator, I just have shifted this peak much more to the north, like around 20 or 22 degrees north or so, with the same solar insolation condition. And in fact, in every experiment which I will show like after this, will have this same solar insolation condition, that's the summer solstice. So it is a fixed kind of a condition with fixed SST boundary condition. The lower boundary and the upper boundary is the summer solstice solar insolation. So this is the pattern. And okay, so this modified SST condition is now shown here. This is the zonally symmetric SST condition. And we are using here the CAOS Community Earth System Model 2.2 Aquaplanet configuration. And as I have mentioned, we have prescribed the SST and the summer solstice condition, and modern resolution is 1 degree at which the output is generated. So this is the typical pattern for the zonally symmetric precipitation as well as the surface pressure pattern. And as you can see, this is for the modified SST run. I have not shown for the 7 degrees north peak SST. So it has just gone to the north of the equator. The extent is well between 0 to 25 degrees north, the tropical precipitation variability. So ITCZ is now to the north of the equator. That's what my aim was, and I have tried to achieve that. And this is the surface pressure pattern, which is expected that to the north of the equator, you have a slightly lower surface pressure, and to the south of the equator, you have a little bit higher surface pressure conditions. But what is our aim here is that we want the South Asian summer monsoon, that is that particular circulation, the monsoon low circulation is required. So for that, what we as you can see that from the ITCZ pattern as well as the surface pressure pattern, you don't get this low or the cyclonic circulation present here. So there are so many papers which have shown that the zonal asymmetry in the surface conditions are important to generate that monsoon low circulation. For example, a paper in 2016, Wu and Shaw, they have used SST wave number 1 pattern. In one part, they have increased the SST anomalies, and the other part, they have decreased the SST anomalies of the same magnitude and try to see the monsoon variability and all other things. Before that, there is another paper by Yano and McBride, very famous paper, 1998 in Aquaplanet. They have also tried the same kind of it. Try to generate this monsoon cyclonic circulation. And this is just from my previous work where I have shown this using energy flux framework. So one thing I just wanted to show here is that the first two panels here, this represents the energy flux equator. I'm not going into the details of the calculations of this EFE and EFPM. Just I wanted to show that this EFE, the energy flux equator, in January and July, the winter versus summer kind of a comparison, where this hatches represents the monsoon regions. And as you can see that in both these seasons, the EFE is well over the monsoon level or near to the monsoon level, except for one region, that is the Northern Africa. I don't know why it has not, the EFE is not able to capture it. This is the energetic ITCZ or the energetic proxy for the ITCZ. And so we can say, of course, consistent with the previous literatures, that the ITCZ, the seasonal meridional migration of intertropical convergence zone, is actually responsible for monsoon, which is fine. But we have also shown that here the zonal asymmetry, the regional asymmetry in the zonal component of the net energy input is also somewhere related to the monsoons. So the zonal asymmetry is also important and is associated with the monsoon. At least the mean also, not the interannual variability, which we have shown in this paper, but the mean condition is also somewhat related to the monsoon. So zonal asymmetry is important. That is the point. So to generate this cyclonic circulation or monsoon cyclonic circulation, what we did is that we have our own this particular zonally symmetric sea surface temperature condition, but here we have provided a big heating over this particular region. Our spatial pattern can be seen over here. So there is a strong heating over here, and we can see that there is an asymmetry because of the heating which we have provided is present. But although here we have given the over this Pacific domain, we have given a very zonally symmetric SST condition. And you don't actually require, as Wu and Shaw have shown, that a wave number 1 pattern, that is part of the globe, half of the globe, you have a positive anomalies of SST, and part of the globe, you have a negative anomaly of SST. You don't require for that for the monsoon circulation. Even in a regional scale, if you give a strong heating compared to the other regions, you can generate the monsoon cyclonic circulation associated with, and the associated feature, which is the North Pacific anticyclone, which is also generated. And in the observation also, we see these two features quite well, like the monsoon cyclonic circulation, cross-equatorial jets, and this as the North Pacific anticyclone. Although weaker, this North Pacific anticyclone looks weaker. We'll compare it with the next experiment.
So what determines the location of the low pressure? Because it's an Aquaplanet simulation.
Yes.
Okay?
Yes.
What does it appear at 30 east?
Yes. So the low pressure is just to the west of it. I have tried using the Matsuno-Gill response also by giving the similar kind of a diabetic heating pattern. And we have seen that this low actually comes just to the west of it. So maybe the Rossby wave response, the off-equatorial heating of that Matsuno-Gill response
What is the distance between that low and the maximum? Is there any clear connection?
No, I don't have that so much of clear connection. Like 105 east, I have given this strong heating. That is the peak of the heating is at 105 degrees east. But it has started appearing around, say, just to the west of 70 degrees east. So, just by Matsuno-Gill response, I can say that it might be the off-equatorial heating response, like the Rossby.
Can you just indicate how many days of integration?
This is I have just removed the first 60 days, and I have taken a 91 days average each.
It remains steady.
Yeah, it's a long time. Yeah. Okay, so now once the monsoon it has been established, now the next condition is that we will impose the gradient in the Pacific, just continuing with this monsoon cyclonic, monsoon heating, and we will try to see that what is the change, what are the changes which we get at least in the monsoon low or this North Pacific anticyclone. That is what our next thing. So now what we have given is that we have this strong heating, the monsoon heating here, and then from the West Pacific towards the East Pacific, and in here, West Pacific to East Pacific, it is a strong gradient is established, which we can see here, heating here, monsoon heating, then from here, there's a nice gradient, which we can see, and then again, it is smoothed towards the same control or the zonally symmetric SST condition. And corresponding to this heating pattern, also we have generated the same cyclonic circulation and the North Pacific anticyclone, but there are several differences compared to the experiment monsoon. This is experiment MG, which represents the monsoon plus gradient. The previous experiment was the experiment M, which is the monsoon experiment. So what are the differences? As we can clearly see that this monsoon low in the experiment M is here, and in the monsoon gradient, it has shifted eastward. So there is an eastward shift of this monsoon low, which will be clearly seen on imposition of the gradient. Second important feature is that the North Pacific anticyclone, its intensity, the high intensity has increased, and the westward extent of this North Pacific anticyclone has also shifted eastward a little bit. So here it was around 120 degrees east, now it has shifted up to 150 or 160 degrees east or so. And if you just take a 5 to 35 degrees north, a long region, a larger region, I would say, for just looking at the cyclonic circulation. So if you just average the rainfall, we can clearly see that there is a shift in the rainfall pattern, particularly the peak of the rainfall from experiment M to experiment MG to the east. We will further go into the details of this. Anyway, so, okay. So this is the monsoon gradient experiment. I just wanted to show that since I have just talked about the precipitation pattern. So in the monsoon gradient experiment, I have this moisture convergence over this region, and this is the net moisture flux convergence. This is the gray line here. This is the del dot QV. So negative means convergence of moisture, and we can see that in the monsoon gradient experiment, the convergence is to the east of the South Asian domain, like 60 to 100. Just to the east of the South Asian domain, we get the strongest convergence. But look at this pattern in experiment monsoon. We have the net moisture flux convergence much more to the west, so around 50 or 60 degrees east. So there is a clear shift which we can again see here, that from experiment monsoon, where it is somewhere in the west, now it has shifted eastward. And the main component which is driving this strong convergence is the zonal moisture flux convergence. And if you take a difference between them, and I have just segregated several components by taking a difference between the monsoon gradient and monsoon experiments and all. So one thing which I want to show that this difference, the anomaly which is coming over here, the strong negative anomaly which is coming over here, or the positive divergence anomaly which is coming over here, is mainly through this red line, which is the Q bar del X of U prime. That is, it is the wind-driven convergence, which is actually responsible for the net zonal moisture flux convergence over that domain. Fine. We have now looked at the monsoon experiment and the monsoon gradient experiment. Now, if we just remove the monsoon and just put only the gradient, then how it will look like. So we just did that, the monsoon heating part, we have just removed, we have flattened this part and then provided a gradient. I have to do this because if we just continue it, we cannot give a proper gradient as we have done before. So I have to flatten this and then put the gradient. And because of that, maybe we have got this weak cyclonic circulation over here, which we cannot associate it with the monsoon as the intensity which we have shown previously. But look at the North Pacific anticyclone. It has strengthened. So it clearly suggests that, therefore, based on the previous experiment and this experiment, that this cooling over this region is actually increasing this North Pacific anticyclone high intensity of this North Pacific high. And moreover, there is also a westward extension of this North Pacific anticyclone, as you can see, to around 100 degrees east or so. And because of this westward extension of this surface pressure to the west, so we have this equator to subtropical meridional surface pressure gradient, which has strengthened the easterlies. So as you can see here, 5 to 35 degrees north, the UG is this orange line. So this signifies that there is a stronger easterlies compared to the other experiments. So the gradient's role is that this westward extension of the North Pacific anticyclone, which is actually resulting into a strong surface pressure gradient over this particular region around 100 degrees east or so, that has eventually strengthened the easterlies over this region. Finally, let me come here to tell the mechanism. I will just go after that. So what is happening is that now we are explaining the monsoon gradient experiments, but I will now split into the monsoon heating part and the gradient part separately. So if we have this monsoon SST heating, just the monsoon response, we get a off-equatorial low, which is the monsoon low, which is present. This is the actual condition. Next, if we just impose the zonal SST gradient, forget about the monsoon, if we just impose the zonal SST gradient, the North Pacific anticyclone, of course, intensifies and it shifts westward, as a result of which the meridional surface pressure gradient increases. There will be strengthened easterlies. Now, this strengthened easterlies, because of the gradient, now will get decelerated because of the monsoon low, which is already present as a result of the monsoon SST heating. So because of that, because of the presence of the monsoon low and stronger easterlies over here, there will be a deceleration of these strengthened easterlies, and that leads to a convergence of the wind-driven moisture fluxes over this region. So this is the region where we are getting a stronger convergence, as we have seen in the monsoon gradient experiment. So this is the reason for why we are getting a wind-driven moisture fluxes convergence just to the east of the monsoon low, which is present originally. Now I will come to this part. So only moisture flux convergence will not give the explanation of why the monsoon low is shifting eastward. You need to prove that there must be some kind of a deep convection or precipitation diabatic heating that will lead this monsoon low entire system to shift eastward. So for that, this little bit of energetics part I have just given to explain that. So if you look at this omega del H del P, that generally gives an idea of the deep convection versus shallow convection kind of a picture, particularly when I have averaged around 91 days in a seasonal average kind of a sense. So we see that to the east, where there is a stronger convergence earlier I have shown, so there we have this very strong positive omega del H del P, which suggests that this region is having a deep convective structure compared to on the other side, on the westward side, it has decreased. So there is some kind of a descent which is happening on the other side. Similarly, if you look at the diabatic heating rate, it has increased. So once the diabatic heating rate is increased, so simply by Matsuno-Gill kind of a response, we can say that if it has increased here, so originally it was here, the peak of the diabatic heating was here, so the cyclonic circulation was somewhere here. Now, because of it has, the peak of the diabatic heating has shifted eastward, the entire monsoon low will shift now eastward. Another way we can see, just by taking a difference between the monsoon gradient and monsoon experiment of this Q net, the net energy input into the column, and the divergence of the energy fluxes. So if you look at this region, here we have a positive net energy input, and there is a divergence of the energy flux. Just remind you that this divergence of energy fluxes generally follow the upper level wind pattern. So there is a stronger divergence, so upper level divergence, and there is a stronger convergence of the energy flux on the other side, where there is a negative net energy input. So this suggests that there is a descending motion on the westward side and there is an ascent in the eastward side. So now if we go here, so we can see that there is an ascent, there is a deep convection over this region, and there is a stronger diabatic heating, which through Matsuno-Gill response will extend the monsoon low eastward. And on the other side, if there is a descent, if there is a stronger descent, so the entire monsoon low will shift eastward. And once the monsoon low has shifted eastward, it will generally shift this North Pacific anticyclone, which has already extended westward, now to the eastward unit. So we have explained these three particular things. That is why the North Pacific anticyclone has intensified because of the gradient which we have provided. Why the monsoon low has shifted eastward? This could be the probable mechanism, which I feel like. So that's why the monsoon low has shifted eastward. And because of the monsoon low which has shifted eastward, the North Pacific anticyclone has also shifted eastward. The westward extension has extent of the North Pacific anticyclone has shifted eastward. So these are the probable mechanisms of how the zonal gradient will play a role in the monsoon or change the monsoon. Finally, I don't think these are all PDF images. I think that's why it is not coming. So I have done some sensitivity experiments also. So they also show the similar picture only. That is, the zonal convergence is consistent in each and every experiment by varying the gradients. So that is somewhat consistent. And even with the sensitivity experiment, we have seen that the North Pacific anticyclone is also the intensified. Or with the decreased gradient, if we change the gradient, we see that the North Pacific anticyclone intensity has also decreased. I don't think the other things will come. What happened? So fine, I will just stop it here. Thank you.
Any questions?
Yeah, here it is called like virtual and the right hand panel. It looks like there's being kind of like whenever you access can you imply that it's actually deciding this one?
Actually, this omega delayed delta generally in the seasonal time scale talks about. I mean, if it is very strong and positive, it gives a top-heavy omega profile structure, and that could lead to the deep convective structure. And this deep convection, as a result of deep convection, there will be precipitation heating over that, latent heating over that region. That has increased this divertivity.
You follow how the SST that evolving after initial condition.
No, I fixed it. I fixed the SST condition. Every there is a fine where we give the monthly SST condition. So every time it is the same SST condition. So that's why only I have used. I mean, just taken 3 years of output. That is enough to stabilize everything.
Yeah, I would like to add that if you're going to use the point static energy framework, don't use the word adiabatic for diabatic heating, because to me it should be part of your analysis. What we call QDIV, that is appropriate, because latent heating is a consequence of convergence, right?
Yes.
So if you're using object, which I know you are using, use the total flux coming from top and bottom, and latent heating is only part of it. It's not separate. Okay?
Yeah.
So that's the advantage of cutting edge approach. So if you're going to explain, you tell us how much is coming from the top of the sun, how much from the ocean at the bottom.
Right.
So you can show what the relative role of those two. In your case, the sun is fixed pretty much.
Yes.
Yeah. So this includes the surface evaporation will play a strong role in your work. Okay. Okay. Thank you. Anyway, it should be a 1 hour seminar. You have a lot more stuff to show. So maybe you'll do a seminar later, because there's a lot more of the time. Oh, got to switch. Yes.
Probably stop sharing and then start. Yeah, just take. You can start it.
Man, it's not coming here. Oh, okay. You can got to press here. I don't know. Yeah, try this. Yeah, thanks. Okay, so at last, yeah, so by today's monsoon almost reached its final point here, but a few days difference is there. So that's a good news. And remember last time we saw that the June rainfall was 40% below normal. Now, if you look at propulsion result, we are only 15%. Just in 1 week, we have overcome. It's amazing. But that news it won't sustain. And the question is why? Yeah. So again, let's compare in June, in minus 38% all India. July is plus 42%, just 8 days. And so that is 15%. So if this continues, things will be overcome. It has happened many years ago, but this year is not sure to happen. Okay? Now, June of peculiar, all the June rainfall is shown here. You can see that only 4 years, 2009, 1905, and 14, only 4 years were below this value, just 4 years. So it's a very unusual June. Now, because of that, it has whole impact on agriculture. So since the monsoon was delayed in North India, you can see that as of 20th June, only 18% of the area sown compared to last 2 years. So this has got a huge impact. Okay. Now the problem is rain has come, so farmers will sow. But the bad news is rainfall is going to stop. So not this, I'll give you a presentation done by University of Chicago, who have a way in which they tell the farmer, don't sow if the rain has come unless you know that there is rain for the next 10 days. That's very critical, otherwise you see it goes waste. So, I'll talk about a very busy piece of work in which they are involved with some farmers in, I think, Telangana, I think, or Andhra Pradesh, and in real time, and they are advising them and they are looking at the differences. Okay, so this will increase after the onset in North India, but if the rain fails in the next 10 days, which it looks like it will be a disaster. Okay, and you look at the spatial pattern, interesting, only 1, 2, 3, well, whole of Indo-Gangetic Plain, small parts of Maharashtra and here are below normal. The rest are all now normal. This is above normal and this is above normal. So it's a unusual distribution because the key states here are well below normal and all of Northeast. Now, what is remarkable about the last 8 days is this. After a period of 1 month, rainfall only once went above normal. Now, 9 days here, you are above normal, okay? And if you look at cold monsoon zone, it's even more dramatic, okay? In central India, it is almost, instead of 7, it's more like 15. But you can already see it is declining. So the value is coming that it is not going to sustain. To me, that is the most fundamental issue. After the monsoon onset, what sustains it for 2 months in a normal year? Okay, this is not a normal year. This is a peculiar year. But a normal year, once the monsoon onset occurred, water vapor has been pumped to the upper atmosphere. It sustains itself for 2 months, but for a few breaks. But this year, after reaching the central Indian air, is going to decline, and it's not clear why. Okay. Now, I want to talk because there are another interesting picture. I saw it. You look at windy yesterday. There was a nice line of clouds just north of Bangalore. These are not rainy clouds. These are a line of clouds which is very peculiar to tropics. These are like birds. You don't see them much. It is there because South India is very dry. This is Foreign Valley bar. Okay. North India is very moist because of deep convection. There's a line here, exactly here. So the dry air and moist air are meeting at the middle of the troposphere and you see a front. But it won't rain. You just see clouds there. That's it. Very nice. You can watch it. This happens in winter also. When cold air from north and warm air from south meet, you find a line of this. Sometimes they take now and then. These are not deep clouds, these are shallow clouds. Okay, now this trough got established in the first week of July. Then we had a low and ultimately a depression and with high water stream. This was bringing rainfall to whole of Indo-Gangetic Plain, Central India in the last 1 week. Okay, so this is a normal thing which happens, but unfortunately, this is not going to sustain. Now, because of this, Mumbai had lots of rain, high water stream here, and winds coming in from Arabian Sea. And I just want to show this picture. I showed it last time. I want you to notice something peculiar, which all of you should always realize when doing any plots. This is a log plot, which I didn't see last time, which is ridiculous. I understand rainfall and large variation, but this is 10,000 millimeter. What is this? It never happened. It should have stopped here. Yeah, in the last 150 years, Mumbai had daily rainfall of 1,000 millimeters only once, close to 1,000. Okay, so 100 could have stopped at 1,000. But when you do that also, it's important to put a note, log scale, okay? Because there is almost no rain here, and there is 300 millimeters in this region. There is the dome area somewhere. So large gradient is there, but in the log graph we don't see it. Okay? So be careful in your plotting. Okay. So I want to also highlight this because we are talking about synoptic system on a day-to-day basis. They are very important to explain what's on day-to-day, but they are totally irrelevant on a season scale. I have been saying this for the last 40 years. People don't believe me. They think I'm crazy. But it is a comment from somebody who did a very good piece of work, Krishnamurthy, whom we know very well from Kola, and as a student from IISc. They make the following comment, which is very, very important. They have studied every low pressure system for the last 150 years, okay, almost. And they have come with a very good paper. See, finally they make this comment. The low pressure system alone may not determine the available response. Okay. So think about it. This is very counterintuitive. They are explaining everything on a day-to-day basis, why this happens, that happens. But on an intangible scale, it doesn't matter. I'll give you a crazy analogy, which people in my age group are worried about. As you get older, you start putting on weight. Okay. Very normal. So your metabolism goes down and your appetite doesn't go down. Yes. So this challenge all of us face. Now, if you look at the Google search, there are hundreds of various suggestions on how to control your weight. So there is a all meat diet, and there is all vegetarian diet, all kinds of combinations. And some work. They are very work for some people, not for others. What they're all missing is the basic energy balance argument. Your weight gain occurs, you eat more calories and you don't spend calories. That's all. If there's an imbalance, your body will have to store them this one. All these other things are detailed, which food you take and what doesn't take. And of course, each person is different. Remember that all of us know there are people who eat like crazy and they are thin. And others who hardly eat and they are fat. Because your metabolism is very different. The way your body absorbs is different. But finally, remember what controls is long-term weight gain is energy balance and nothing else. Okay? So many people who go on diet, they go on yo-yo. They'll go on a diet, they'll come down, they'll come back. Because your body, your brain has a central control system which decides what should be your weight. Now, one thing must know, from evolution, the last 100 years is very peculiar. Most of us who are not poor have access to food all the time. Your fridge is there, you can order online if you think you want. This was not true for the last million years. Your body has evolved for the last million years to worry about famine. Famine was very common everywhere. Okay? Death by famine was the most common cause. So your body has a control system which says put on more weight. So that when there's a famine, you will not. So I remember 50 years back in arranged marriages, the mother-in-law will demand a girl who is fat. You may think why? Because in India, famine was quite common, and they want to make sure that a girl is healthy. So this point is that today, when we are situated, we have too much food around all the time, and of course, the body wants it, but it's what is called control point always is more than what is required. Okay? So the energy balance is always in the favor of having more weight in your body. Okay. Now let's look at what happened in the last 1 week. I would say that the rainfall for NCR is quite good. There are a few days are off. It correctly got the increase in rain and slight decrease in the last few days. Okay. Now, the prediction of today is very interesting. It says it's going to decline and then it's going to increase. Now, this is not true in all models. So this is where the surprise will come. Some models will show decline. I don't know who is right, but this decline you will see in the next 2 days definitely. Then there's a revival in this model. But you look at our CFS-V2 CFS model, it is not doing so well. This is observation. This is the last week. It is not doing so well. It is overprinted this rain. Okay, so not been pretty rain yesterday, quite well, even today. So this model now telling us, I'm sorry, it's telling us there will be huge decline. Okay? So we'll see next week who's right. Whose short-term forecast is right? It's only 1 week forecast. It will depend only on the kind of assimilation I've done, and we will see who gets it right for the next 1 week. Next week, okay. Now I come to the most important paper, I think, which is not severely cited. This is a 15-year-old paper by T. N. Krishnamurthy, a legend in synoptic analysis and monsoon. People give all kinds of reasons why the break occurs, why active occurs, upper level, this, that. He has got a very simple, beautiful reason which I like. You will not like it, but I think this is the best reason. What is that? He is arguing that during a break period, low level moisture comes from Arabian Sea, and the mid level, 700 millibar, comes dry air from mid latitudes. And this prevents storms from forming. We have enough moisture on the ground, but that has to go up. It cannot go with the dry air on top. Okay? So to me, there's a very neat result run by trajectory analysis, no correlation, no all this commercial that goes on the field. He's just showing you by example that this occurred. This is a break period on 2002, the famous period we talked about. This, but the question, of course, is not said why this came. That is still an open question. Why did the air come from the mid latitude at 700 millibar? Not at upper level. Now, a lot of people talk about Ross period and so on. But finally, you must explain how the 700 millibar wind is coming from the north. Okay? Now, this is the active period. You can see all the trajectories from Arabian Sea. So that is the clean difference that you see between a break and active. And I would like some of you to this year, if you're going to have a break in the next 15 days, please follow the analysis and tell me whether this is happening or not. Because I would like to know whether this is works. I mean, he has given many examples. I've only given 2. But he gives us a complex system. Doesn't mean every time it will happen. So let's see this year if there's a break in July in the next 15 days, whether it occurred due to a question of dry air. But this is the key originality here. He didn't look at 850, he looked at 700. At 850, you will not get air from north because there's a mountain there. That's about the Arizona 25 years ago. There is enough mountain west of the east which blocks low level air. Okay? But air can come at 700 millibar because not all mountains are that high. So this is a very interesting idea. So I think this should be, people should read this paper and see how many break cases are like this. He has given about 4 or 5, but I think every break should be looked at. Because this to me looks like the simplest idea, but of course you have to explain why that air came from there. That may be connected to Ross-Begue, but Ross-Begue normally people talk at 200 millibar. From 200, you have to tell me how 100 looks. Okay? Now there's a surprise from the Eastern Korea. We have the latest forecast, long term, on 1st July. Okay? Now remember what I showed you the first day and so on. It is very different. Notice July is above normal. Okay? This was not sold 1 month back. 1 month back, they said it will be below normal. Okay? So that means this should be playing some role. So when they went from June to July, something changed, and suddenly they're saying above normal. And well, this is very interesting. Then August is below normal, which was, look at September. That's shocking. September is below 2 sigma. Okay. So we remember this forecast, we see it in September. whether Eastern River got it right, because this to me is very unusual. It means in that model, the ENSO is playing a dramatic role in the month of September. Okay. Otherwise, I cannot say why it should go well above even this climatology of hindcasting they do is going well above that. Okay. So this is a very good result. I not understood why from June to July there's such big change. Okay. Now, another quote I want to give from Wallace. Wallace is the most well-known person. All of you read his book, Wallace and Hobbes. He makes a very interesting remark that the paradigm of perturbed equatorial circulation cell is too simple to explain endosphere. I like it very much, but I already believed in it, but nobody agreed. Everybody talked about Hadley and Walker and so on. He said, no, not that simple. The equatorial circulation perturbation cannot really affect rainfall. Okay, please read this paper. It's a bit complicated. Wallace was mastered in using years and pieces and so on. You have to go through that paper, and I don't think he's explained it. I don't know. I sent you the paper. I don't think he's explained why. Right? He just makes a statement. I'm not sure an explanation of why he's against it, but I think he's right. Okay. Now let's look at the Pacific Ocean last week. You can see that there's a large, warm equatorial region, but there are also other regions which are unusual anomalies. Okay. So this is what my contention is. We have been focused too much on NINO 3.4. That's because correlation is high. But that doesn't mean the rest of Pacific Ocean is not playing a role. It's playing a role. And what Sujatra showed just now is a very good example. Slight change in the gradient in the Pacific Ocean has a huge impact on Indian monsoon. Okay. Somehow that has not been given enough importance. So I'll highlight that a little more clearly. Now, this is an very interesting example. Average over West Pacific, okay, from 97 to this year, along the latitude, okay. See the difference between 97 and this year. They are totally different, okay. Connection is absolutely, nobody talks about it, I don't know why. There's a dramatic change between the 90s and now. Now there is warming all over the tropics, everywhere. Here, actually, according to this picture, it is, except for the El Nino period, there was a La Nina, I think another La Nina. But the point is that if you are trying to understand El Nino connection to monsoon through correlation, all this will come into play. It will not take into account the peculiar feature of the last 10 years. Okay? From here, the last 10 years, both southern and northern Pacific Ocean have gone. Okay. So this I just got it. I'm not looking at detail. There's something additional there which is connected to what Sujatra is saying. We will discuss it maybe subsequently. Okay. Now let me give you my point. So I did a correlation between the SST in the West Pacific, which we normally know, okay, and the velocity potential at Total Bolivar, or 0.2 sigma. 0.2 per sigma. Now, what is it saying? This is saying that if this temperature here, everything is correlated to this temperature here, right? Okay. Now, it doesn't cause this is all ascent related to this. So, look at this plot, and I'll give you the next plot. Keep it in mind. Next plot is NINO 3.4 with velocity potential. Okay. See the difference in the color. Here is descending over India and Indonesia. Is well known. All of you know that NINO 3.4 causes descent over the this region, much more stronger over Australia than over India. But this specific anomaly has the opposite. I don't know why. Somebody has to figure out why West Pacific anomaly does something very different from NINO 3.4. Okay. I've not fully understood why this is happening this way. Okay. Now, this is what people normally show. Standard. And this is also very interesting, I tell you. Somehow, date line is the dividing line of this world. Okay. During El Nino, to the right of the date line, you have ascending motion. To the left of the descending motion. It is not equatorial. It is entire 60 south to 60 north. This is something nobody talks about. This is very peculiar. This is not just a local circulator. This is a whole world is in two parts. Okay, you can go to 90, one can go up to 90. Also, it looks same. I don't know why. So the fact is that this anomalous descent and ascent extends right through the middle latitudes and even the polar region. This is the signature of 3.4. This is the signature of Pacific warming. You want to understand the net impact, you have to add the two somehow. I don't know how to do that. Okay. Now this is my September. This one. September is the strongest relation. Now I'm not done 3.4. I've done rainfall over India. Now why I've done that? I wanted to show that rainfall over India, when it's above normal in September, actually has anomalous ascent and descent over this region. This is very interesting. This is very preliminary. I've not done enough. But do some lead lag. What it says that the rainfall in September is high, okay, which it won't be this year, but if it's high, it will prevent 3.4 from having high rainfall. So this will cause a descent over that region, broadly, not equatorial alone. Okay? And the maximum is not on the equator, it's off the equator. Okay? So this is the point. Although the correlation between 3.4 Indian rainfall in September is the highest, 0.8, 0.9. You can't believe it. Okay? But it doesn't prove that 3.4 is causing September rainfall. You have to do much more capital analysis to show how they interact. Right? So India can also have influence on Pacific, so does India. So this is, I've done it just to show that you plot the September rainfall over here, will look exactly like this. I'm sorry. Exactly like this. Yeah, I'm sorry. This is how it looks like. I'm not done it. You do only September. It's actually stronger, this connection. But rainfall thing looks opposite. The two are going to interact each other and decide what will happen. So if you believe the ECMWF forecast that September is going to be very, very low, it doesn't mean that 3.4. It means that for whatever reason cause a low rainfall in September actually will enable 3.4 to go even higher. Okay? As a matter of fact, I forgot, next time I'll show you. There are some models who are showing 3.4 maximizing this year in September and then declining. I don't know why, because all of you know that normally maximizes in December or January. But this year, some models are saying September it will peak and go down. We'll see what will happen. Okay, I'll end on an interesting comment. Today, this year is the 50th anniversary of the establishment of ECMWF. It was celebrated. It's one of the best centers in the world. They provide the best forecast. Okay. And their analysis is the best right now. Okay. Now, president of this data center of ECMWF, Florence Rabe, gave a very nice quote, which is worth mentioning wherever you go. Okay. It is that there are few other subject areas that offer a combination of excitement, challenge, and tangible impact. Okay. Now, somebody may ask, you're so smart. Why not in astronomy? Astronomy is a great field. I can tell you, I love it. There's no impact on my life. There may be a black hole there, there may be exoplanet there. Doesn't matter. Okay. It's fun, like fiction, but our field, weather and climate, has impact every day, every week, every month, and every year. That's the point he makes, and that's a very nice point. On that note, I will stop. Now, any questions? So many of your parents are aware of doing that in terms of disabilities. Okay, yeah.
The SST is sold to 97 to this year. The homework papers.
What?
The logs from SST 97 this year.
Yeah.
Was it detrended?
Was it?
Detrended.
I don't know. That's not. I just put it just. I didn't check it. I was going to check. Yeah, I just saw it. I thought I'll put it up. I think it was
linear.
Yeah. It may have the trend part. Yeah. Because long one is occurring, the trend part will be there. But even then, I wanted to focus on the north-south variation, not the timeline. North-south variation is different. Okay. That is the point I want to make. Yeah.
I should take a lot of ideas from the I should take a lot of ideas. We should get more like
Oh,
standard.
yeah, very much.
Break the example.
Yes, but this year, this year they are saying September will be bad. But how much September?
Let's see that a lot of people actually. A lot of people just in creating already.
Yeah,
Are they excited about it? But a lot of people.
yeah.
But yeah. Being always in intelligence.
Yeah.
And so is exactly. It's almost helpful.
Yeah, that's, yeah, I just made a plot, I not fully understood what it is. Maybe I'll put one,
So big.
Yeah.
What we like ours. Just thinking, and we notice this.
Yeah, that's something.
Not bad.
Okay.